welcome to class number 26. Our goal for today is to solve for the normal force acting on an object. So our do now is just a quick little review of what we did last class. It's a free body diagram question. So we got a fish and it's on a, let's see, you're fishing and you catch a fish with a mass of 4 kilograms. One thing I didn't mention in this question is that it is a fish out of water. All right, so you don't have to worry about buoyant force or anything like that. So if the fishing line can withstand a maximum tension of 50 newtons, what is the maximum acceleration? You can give the fish as you reel it in, draw a free body diagram of the fish. So here's our fish. All right, we got to think about the forces acting on it. Well, we know weight is pulling it down, or the force of gravity. So we can call that, I'm just going to call that weight, or you can call it FG, whatever you want. And we know that the fishing line is pulling it up. Now you can call that tension, or you can just call it the force of the line. We have to make weight negative because it's pointing down. And, well, we know our equation for weight, right? So weight is equal to mg. So the weight is equal to 4 kilograms times 9.8 meters per second squared. So our weight is equal to 39.2 newtons. So there's our free body diagram. I'll plug in the 39.2 newtons down here. So now we have to go to our equation, A equals F net over M. The acceleration is our unknown, F net. Go to the free body diagram, grab those forces on the free body diagram. Oh, by the way, I just realized the force of the fishing line, we just said the maximum tension in it is going to be 50 newtons. So that's 50 newtons there. Okay, so that's not an unknown. So our F net, we just do 50 newtons plus a negative 39.2 newtons divided by 4 kilograms. Throw it in your calculator. You should get 2.7 meters per second squared. All right. So this other do now question is kind of what we're going to be talking about today. So it says draw a free body diagram for a 10 kilogram box sitting on a table. So here's our box. Okay, and it's just sitting on the table. So we have weight pulling it down, negative weight, and we have the force of the table pushing it up, F table. All right, so we know the weight. The weight's equal to mg. And in this case, m is 10, g is 9.8, so the weight is just negative 98 newtons. All right, so let's go to our equation, A equals F net over m. So the box is just sitting on the table. Okay, it's stationary, not accelerating up or down, nothing. So the acceleration of the box is going to be 0. F net, just go to your free body diagram. You have F table plus negative 98 newtons all over the mass, which is 10 kilograms. Cross multiply, 0 times 10 is just going to give us 0. And we have the force of the table minus 98 equals 0. So the force of the table has to be equal to 98 newtons. All right. So this force of the table pushing up the box actually has a name. It's called the normal force. So in math, normal has a meaning. Okay, it doesn't mean regular or ordinary. It's not the natural force. Normal means perpendicular. If you remember this symbol from math, I'm going to be using it to mean perpendicular. All right. So, and I want to be more specific about what do I mean by perpendicular here. The normal force, F subscript n, is always perpendicular to the surface the object sits on. Now, very frequently in this course in Regents physics, the normal force is equal to the weight. It's not always the case, but 95% of the time or so it is equal to the weight. So there are 3 criteria, though, we need to satisfy for it to be equal to the weight. First, it has to be on a flat surface. Okay, most cases we're dealing with flat surfaces. If you've seen an inclined plane, then you know it's not equal. The second criteria is that it cannot be accelerating up or down. Cannot be accelerating up or down. And third, there can't be a third force in the vertical direction. There can only be normal force in weight. All right. So in number 2 here, it says we have a 20 kilogram box sitting on a table. Find the normal force acting on the box. So we can start it with a free body diagram. So here we go. We have normal force acting up on the box. That's what stops it from hitting the ground and falling to the center of the earth. So that's normal force. And going down, as always, we have the weight, which is equal to negative mg, which in this case, m is 20 and g is 9.8, so that's 196 newtons. So when you think to yourself, is this a case where we are on a flat surface? Okay, so yes, we are on a flat surface. Is this object accelerating up or down? Is it like on an elevator or anything like that? No, it is not. Is there a third force in the vertical direction? Is someone pushing down on the box? Is someone pulling up on the box? No. Therefore, we can assume that the normal force is equal to the weight. Okay, in this case, mg. So the normal force equals 196 newtons. Like I said, 95+% of the time, normal force is equal to the weight in this class. So this is actually a case where it's not equal. Think to yourself why it's not equal. Well, notice it is not sitting on a flat surface. Okay, so the question is, which force represents the normal force? Remember the definition for normal, okay, perpendicular to the surface. So which one of these three forces is perpendicular to the surface? It would be force A. Okay, and the reasoning, A is perpendicular to the surface the object sits on. So there's our basics of normal force. We're going to be practicing this a lot over the next few classes. So if you have any questions, let me know.